Welcome. So before starting, I'll just tell you something about the course timings and what will be our agenda today. So the course name is Unconstrained Optimization. So basically, we optimization is the go-to technique. It's at the heart of almost all of the engineering branches, and it is useful in several other scientific science branches also, apart from engineering. And we are going to look at part of it, like unconstrained optimization, which does not have constraints. So optimization of nonlinear functions without constraints as a first part. Maybe later on, after these series of lecture, we can continue with the constraint optimization as well. Uh, the course timings will be every Thursday, 3 to 4:30 p.m. If this is unsuitable for a few people, we can change this. But I think that discussion we can have on the mailing list. Um, and then the agenda for today is we'll try to derive some basic definitions related to optimization. We'll look at some of the basic optimization problems. So these will be very introductory problems, and we'll also see some applications in the real world scenarios today, and some popular examples as well. And then we'll briefly look over how to solve an optimization problem. Like this will be an overview today, and we'll deeply go into in the upcoming lectures. So we'll look at how do we formulate a problem and how do we solve a problem, and especially we'll go deep into these graphical methods. Uh, and then at the end we'll go at for the course overview, that steps or like what all are we going to study in this course, and then I'll provide some references about the books that you can refer for studying this course. So with that we'll start with the course. And the first thing is like optimization in daily life. So optimization in daily life, there are several problems where we try to use uh, optimization subconsciously. So for example, diet or choosing what to eat is an optimization problem that we are continuously solving. Like how what food should we eat so that it satisfies our taste as well as give us enough nutrients, and also does we do not go overboard on the calorie count. This is the kind of thing we keep on doing daily. Then one of the problem that we try to solve is the travel problem. So most of the time we are trying to go from point A to point B in a city, and these days we have Google Maps, but sometimes people do rely on their own experiences, like which way to take so that I can avoid traffic, so that I reach the place in the minimum time. There are several other problems like exercise problems. So how much so someone is going to gym, how much weight should I lift today so that I have not I optimize the pain as well as my growth in terms of my muscles or my stamina. So all these things we continuously solve optimization problem uh, in our daily life, and we want to study these problems formally in this course. So uh, so first thing, we'll define some definitions of terminologies uh, related to optimization. The first one is like optimization itself. What is optimization? This definition I took from freedictionary.com. So there it says the procedure or procedures used to uh, make a system or design effective or effective or as functional as possible. So this is just what we talked about. That optimization is like something, the things that you do to take some decisions, which will improve the quality of what you are trying to do. So that what's it trying to say in English. This is an informal definition. So then you might some people ask why optimization. So optimization helps us taking a better quality decision. So when you're trying to uh, go from point A to point B in the city, you're trying to improve reduce the time, because for you that is important. Same thing when you are trying, let's say you have some money and you want to invest, so you want to invest in some commodity or stocks which will I mean increase your gain to the highest, like you want to maximize your wealth, and you are trying to solve that optimization problem using what are the growth rates of individual stocks. You look at that, and in that way, in somehow you're trying to improve the quality of your decision making. So it improves quality. And uh, and there are several applications in various branches of science. Like engineering is one of the, like it is at heart of all the engineering branches. Almost all the engineering branches use optimization somewhere, maybe formally or informally. There is always optimization involved. It's also used in business, taking business decisions, economics. It's used in science and military applications. It also used in robotics, control, etc. So there are several branches of sciences where optimization is used. Now, moving ahead, this getting rid of this informal definitions, we'll now move ahead and define what is a mathematical program. So before defining it, I just want to clarify, I'm not talking about a software program. Because many people, when they read the term program, they think there's some kind of code that is involved here. This is a kind of a misnomer, because these theory of optimization had started before the advent of computers in the mid 20th century, and uh, there they started using this term called mathematical program, even before even before the invention of these computers. So actually this means very different from a code, and it's not same as a software code, which people generally call program these days. uh, uh, so a mathematical program is just a mathematical formulation of the optimization problem. So what does this mean is, like, if you have some problem, something to optimize, as soon as you write it in terms of mathematical formula, or you write it as in some form of mathematics, then we call it a mathematical program. And it turns out that almost all of the optimization problem can be written in this form. You can minimize some objective function fx subject to x belonging to some feasible region. So here x is some variable. So basically, X are some decision parameters that you have to decide to take the best decision. So and fx is the objective function. So it is some quantity or some physical quantity which you have interest in. So like say for portfolio maximization or investment, it's your wealth, how much wealth you can increase, or for traveling problem, it's the time, how much time can you reduce. And similarly for diet, it's like which what is the most it's which will give you the most taste, or maybe which will give you the most nutrients, which food will give you the most nutrients. That can be your objective function. And S is called the feasible region. So what does this mean is like x takes value. So in generally in mathematics, x, your variable will be some number, some real number or integer, and it takes some values from some feasible set. So for example, let's say your parameters in your diet is what kind of food you take. So as feasible region may be the food that is available. So all those kinds of things in maths, let's say x, so s can be any set through which x takes the values. So if you can, as soon as you write some objective problem in this form, it becomes a mathematical program. So now we define mathematical program. Now let's define the solution of a mathematical program. So solution of a mathematical program can be written as x star belongs to S, such that see, just before moving ahead, I'll read the statement, but I want to define some of the symbols that I'm using. Uh, so some of you might not be familiar with them. So this symbol is basically a shorthand for saying for all, and this symbol is a shorthand for saying belongs to. So most of you might know this, but if you don't know, I just wanted to clarify. And so basically, when I write for all x belonging to S, this means that for all the x who are in S, this statement is true. So now let's read this statement. So x star belongs to S such that uh, fx star is less than equal to fx for all x belonging to S. So what does this mean? So here x star is the solution. So a solution of a mathematical program is such a point in S such that for that point the objective function value is lesser than the objective function value at all the other points in S. So that's what the solution means. I think it's a fairly obvious. It's just a way how you write it in mathematical terms. That's what I've done here. But in English, if you convert this statement into English, it's fairly obvious. So basically, it's the value where the fx gets its minimum value. So fx star is optimal objective function value. Now, there is one point that I want to say. Let me write it in red, or let me write it in blue. So x star may or may not be unique. So this is one point. It does not mean like if the solution exists, it has to be unique. It may not be unique. There can be multiple points for which the functional value is same. And the second point is x star may not even exist. So it's possible that the mathematical program that you have written may not have a solution. So how is that possible? Let me give you an example of both of these. I think it's very intuitive to think of a solution like this in a problem like this. So let's say I have this function uh, in which this x-axis represent x and this y-axis represent fx. So for this problem, there is no minimum exists. So these are going to infinity on each side. So this is basically a quadratic function. Uh, so for this, no minimum exists, uh, which is very low. Even though the maximum exists here at this point, but there is no point in this line x for which all the other points have higher functional value. Then the other is for the solution to be not unique, it's fairly possible to have a function like this. It's curved, then it becomes a straight line, and then it again becomes a curve. So in functions like this, all these points have same objective function value. So for this, all of these points are the solutions. So solution here is not unique. Okay, so this defines mm, uh, s- what is a solution of a mathematical program means. Now, I just want to give you one note here that you might have seen that sometimes the optimization problem is about minimizing something like how like we want to minimize time from going from point A to point B. But there are also problems in which we want to maximize something like investment. So we want to increase the money that we have invested. So for that, uh, I will tell you that all the maximization problem can be converted into minimization problem. So so as you can see, if there is an objective function fx and we take its negative and find its minimum, then we actually finding the solution of this maximum fx problem. And we then again do the minus to it, like a negative to it. So we'll find its maximum objective function value at that point. So every max, so if we solve this minimization problem, we are anyway solving this maximization problem also. So what do I mean by this is all maximization problems can be converted to minimization problems. Okay. So that is the thing. But the question is, can all minimization problems be converted to maximization problems? Is this possible? So this is something to think about, and I'll let you think about it, and maybe we can discuss this in the next class. So can I write all the minimization problem as maximization problems? And so going uh, beyond this is one more thing that I want to tell you before going ahead is notation. Uh, let me, so so as I wrote there, minimize fx subject to X belongs to some feasible region S. This is very long, right? So in mathematical notation terms, I can write this it like this: minimize over X, Fx, uh, subject to X belongs to uh, some feasible region S. This is how you will find a mathematical program written in most of the books, mathematical books. But whenever you see this, you actually read it like this in English. So that's the thing. Now let's move ahead. So we defined what a mathematical program is. Now let's define uh, what is mathematical optimization. Or programming. What is mathematical programming? So again, I will say this point quickly that here programming doesn't mean writing a code. It's actually solving or it means something which we'll going to define. So it's basically trying to find a solution to that mathematical program that we wrote. So here you might say that we already defined optimization above, right? So that was an informal definition. Now let's try to define it mathematically. So let's call this problem one. So study of problems of type 1 like this. Uh, so what do I mean by studies? It's like existence of solution, algorithms to solve the problem if exists, and analysis of solution is called mathematical optimization. So basically, we have some rough idea in what optimization is called. We have defined what mathematical program is, and now mathematical programming or optimization means we try to find if this problem that is defined by one has some solution or not. If it has solution, can we derive an algorithm or to solve the problem, or can we solve this problem? And once we solve the problem, we want to analyze the solution, like how accurate is it, how fast can we get to the solution, all those kind of things. Can I make this algorithm change the algorithm such that I reach the uh, I reach the solution faster even though I don't care about accuracy, or can I change the algorithm in such a way that I don't care about the time, but the accuracy should be super high. Can I change it in such a way that both are good, like accuracy as well as time taken? So all those kind of analysis is a part of mathematical optimization, and this is what we are going to study in this course. So till here, I think, is there any question? Because we'll move to the examples now. Some examples that some preliminary examples. Okay, I don't think there are any questions, so I'll move ahead. So before uh, like some optimization problems, so one of the very common problems is shortest path problem. So let's say there are 2 points A and B, and uh, you have to find the shortened distance, shortest, you have to find a curve that gives you the shortest distance between these 2 points. Uh, so as we all know, in a 2D plane, it's always a line, straight line joining with the 2 points. So it's fairly an obvious problem. So this problem can be posed as an optimization problem. So if we assume Euclidean distance, like these are some that intuitively you know that this is the solution, but in we can pose this problem like considering Euclidean distance and trying to minimize that problem, because there are infinitely many curves passing through these 2 points, and out of those this is the curve which gives you the shortest Euclidean distance. So that's one of the problems. Then there is uh, so this is a very simple problem to solve, but let's assume that this problem can be made more complicated and interesting. So let's say there is a dense connection of roads on this on this uh, map, and you have to decide what is the best path to take to get from A to B, because there is no straight line road going from A to B. So then how do you solve that problem? Then the problem becomes a little bit more interesting. And so that uh, if you add roads, now if you also add traffic in the problem, it becomes more interesting. Let's say we want to optimize the time. So this is what is generally done by Google Maps. So there are several other parameters. These are just generic two most important parameters I think that Google Maps uses, but it tries to optimize the path from a point A to point B. Okay. Hi Sanjay. So I think we have already like defined a few initial terms, and we are on to the optimization problems. So I'll share the notes. Don't worry. Till then, I think I will continue because. So so I was saying that from point A to Google Maps solve this optimization problem of, from going from point A to point B through roads, through traffic, etc. Now there can be in example there is one more there is another problem called bus stop location problem, right? So let's say there is a road PQ along which we have to build a bus stop. Okay, it's called the bus stop T. It can be built anywhere along this road PQ. Okay, and the way it has to be built is like, let's say there are 2 points A and B, population dense points. So we have to build the bus stand in such a along this road in such a way that the distance between A and the bus stop and B and bus stop should be minimum, the sum of the distances. So that is a good problem statement to have. Minimum distance from bus stop. So actually you might have solved these problems in your class 10th or 12th through geometrical ideas. You can solve it that way, but this problem can also be posed as a optimization problem. So basically here you want to optimize the distance from A to T and B to T, straight line distance for now. And if you want to make the problem a little bit interesting, then road can be curvilinear rather than a straight line. And also you can add roads from A to bus stop or B to bus stop rather than straight lines. So all these things will make this problem statement interesting. So this is one of the problem statement where optimization can be used. Now, there is one problem that you all might remember solving it in your maybe undergraduate years or school years, is like when shortest time problem, time to fall problem. So let's say I have a vertical plane. Okay, so this, let's say this is X, this is Y, this is, and this point is O, A. Let's say I call this A. Let me call this O. And there is another point P here. So the task is I have to find this curve. It can be any curve of fx and fy. I mean, this can be any curve like y equal to y equal to fx is this curve. I have to find this curve such that the time taken by this ball starting from O and reaching P is minimum. So minimize time from O to P, and the thing is it has to fall under its own gravity only. There is no external force, no friction, etc. It has to fall under its own gravity. What is this curve so that the time from O to P is minimum? And a very intuitive answer that people give is it's a straight line, but as it turns out, it's not a straight line. It will be a good problem to solve it yourself, or maybe you look up this problem online. You'll find that this curve does not turns out to be a straight line. It is some other curve. You might have seen this problem in your undergraduate years. You might already know the solution, but yeah, it's an interesting problem, and it can be posed as an optimization problem. Like it can be, optimization can solve this problem very easily. Then some other kinds of problems are facility location problem. In a way, this is similar to that bus stop location problem. Like let's say I have a population dense area, uh, and let's say these are four population dense areas where people live, and we have to decide where should we build this convenience store such that the distance between these population store is the minimum. So minimum distance problem. So this is similar to that, but uh, this is also a very good problem to solve. So uh, there is another variance of the problem. So let's say you have to decide the garbage dump area. Then in this you'll have to define it should be maximum distance from population areas. Within some boundary of the town, of course, like it has to be inside some boundary, but it has to be maximum distance away from the population area. This is a very interesting problem to solve in terms of, and this can be solved using uh, uh, formulation, and solution techniques. And then it can be also be seen that commodities handling can also be uh, commodity handling or transportation problems or commodity transportation problems. So this is a uh, uh, this is a very common optimization problem to solve. So let's say I have two uh, plants or factories that produce fertilizers, okay, in kgs, let's say kgs, and I have three retail stores, okay. I have three retail stores, and I can go to fertilizer has to go to all three of these retail stores to be sold. And let's call this R1, R2, R3. Let's call this F1, F2. And let's call the amount of fertilizer that is going from F1 to R1 is X11, from 2 to 3 is X23, and similarly all the rest of the problem. So let's say these have some supply, or let me use the term capacity, these two. So each factory has some capacity, weekly capacity, uh, to produce some fertilizer, let's say 1000 kg each, or 1001, 2000 the other. And each retail has some demand. Let's say some demand is required, and you have to optimally distribute these what how the commodities should go from F1 to R1, F2, F1 to R2, and so on, such that it's like it is the most convenience, or it's the best way. So we have to define that best. Maybe going from F1 to R1, the roads are not good, so cost will be high. Let's say F2 to R3 is very close, let's assume, so that cost will be low. So what should be the commodity transfer such that this uh, the retailers like suffice their demands, it is does not overflow the capacity of each factory, and also the cost is minimum. So this is a very interesting problem to solve, and we'll try to formulate it later in the lecture. uh, so One more thing that makes this problem interesting is, let's say F1 is making continuous. So F1 is making fertilizer in kgs, and that is a real number, let's say. So fertilizers is in real numbers. But let's say F2 is making seeds, packets of seeds, and that is an integer, or a natural number, seeds. Then if you see, the variables involved become continuous and discontinuous, or continuous and discrete. So it becomes a bit of difficult problem. So in which some variables are continuous, some variables are discrete, and these kinds of problems are called mixed integer programming, or MIP, sometimes it is called. So it's a different branch of optimization, in which, so you it can also happen that all of the variables involved are discrete. So for example, one of the examples is, let's say you have some motor M, and you have to design some gearbox, like let's say some uh, which has some gear, has some tooth. If you are from mechanical background, you might know. So what should be these teeth? So here teeth are discrete and not continuous. So what should be the teeth to get the maximum output, maximum torque output? So this can be a very good problem statement, and constraint can be the weight of this gearbox. So let's say weight should not go beyond this point. of the gearbox. So if you keep on increasing the uh, of the tooth number of tooth, the weight will increase. But your weight will also increase. So weight increase, output will increase, but weight is also increase. So we have to uh, minimize the weight, but like keep the weight under some restriction and maximize the output torque. So this is a very good optimization problem to solve, which uses discrete variables. Now, moving ahead, one of the most like one of the most important class of problems that optimization solves is data fitting problem. It is I'm saying uh, I'm saying this that this is very important because this is one of the most important problems, if not the most, because this is what is being used these days to learn all these neural networks. So, machine learning problems. So, in which they get some data, observe some data, and they have some I'm like simplifying the problem, but they have some neural neural network inside uh, as their function predictor, and these neural networks have some weights. We call them W, let's say, some parameters. So let's say they take in, that convert input to output, and we get a lot of input as data. Let's call this X, and a lot of output as data. Uh, and we want to uh, learn these values of weight such that the uh, we get some relation between input and output, and we learn the model. So basically, when we say we want to learn the model, it means uh, we trying to reduce the error. So we assume some function which is a neural network, and we try to modulate their weights in such a way that the error between the observed data and the data given by the model is minimum. So we want to so as soon as minimum comes, we want to minimize that objective function, and we want to find those parameters is minimize that objective function. So that's what these days people are doing, and most of this theory is used to train neural networks. Theoretical unconstrained optimization algorithms are used. So this is one of the most important application of optimization these days. So let's discuss one dummy problem here. So let's say I have bunch of data, this X, by it's single variable, single input variable and single output variable, let's say. So let's say this is the data. So these point X and Y. So each point represent a pair of sets, uh, a pair of sets x1, y1, etc., etc. And we observe this data and we try to get a model, let's say fx is equal to y bar. Let's say so it looks like a quadratic function. Let's assume y bar is equal to ax square plus bx plus c. So we assume that this is the model with unknowns unknown parameter a, b, and c. So what we do is, and now we have these x and y data. So what we can do is we want to, based on the data, we want to find what is the most optimal value of A, B, and C, such that the error between what this model predicts and what the data we have predicts for the same x is minimum. So this is what this problem statement means. like this is what people do. This is called data fitting problem most of the times, and these days it's also called learning. So yeah, so these are some dummy or some useful examples, but small examples that give you a good idea of how what kind of problems do we see in optimization theory. Um, there are some other problems also, like I'll just discuss from surface level, like diet problem that I discussed with you initially. Then there are some portfolio allocation problem, uh, which means like investment. Basically, this is what means investment. Like you have a bunch of money, you have bunch of, like you have some stocks give with the rate of history of their rate of growth given. Now you have to predict how much a fraction of your wealth or investment, or your sum should you invest so that you maximize your outcome. So that is an optimization problem. Like engineering design. So as I told you that gear example, it can also happen that sometimes you have to design a part. Let's say you have to design some mechanical part in which constraint is weight. So it should not be very heavy, and objective function it is like it should take the load, as much load as possible. So this is one of the classic examples, that weight versus load. So it should be able to take the load of whatever it is will be giving, but for taking that load, its weight should also be as minimum as possible. So this is a classic optimization problem, and a lot of people use optimization techniques to solve these kinds of problems. And then there are application in robotics. So one of them is path planning. So let's say an autonomous robot has to move from point A to B in cluttered environment, let's say an office environment. So what path it should take so as to avoid obstacles and also reach there in minimum point. So that is path planning, in which you have to plan your path. Uh, Also, you have to like it can. So it sometimes time is not issue in robot path planning. Most of the time, it's safety. So what path you should take so as to maximize the distance between all the obstacles. So that can be one of the optimization problems, and problem becomes interesting when obstacle is also moving and you are also moving. So that's where the problem becomes really, really interesting, that how should you move, how should you plan your path in the future, how in the future, such that you do not you avoid all the obstacles, be at a safe distance, and also let's say in the middle the trajectory of some obstacle changes, then how do you adapt. Those kind of problems are really interesting in robotics. Some other the other application in robotics is trajectory optimization. So in this, let's say you have given robot a trajectory, desired trajectory to reach, and you have some model of the robot. Let's say how the physics of the robot, how does it perform, but that is not accurate. Let's say like it is not exactly, you cannot model most of the things in the real world, like friction and many other things. Let's say it's not ideal. Then you have to uh, design the actions or the input. So let's say you have some input u to the robot and it moves through this trajectory. You have to give u in such a way that the distance between the given trajectory and actual trajectory is minimum. So that is also an optimization problem that people solve. And uh, if we get time, we'll see in the future lectures one of such examples. So I think that's it for the examples now. Yeah, so I'll quickly go through steps to solve the. Any questions till now? I think this was fairly preliminary, and most of the things of these things you know. So yeah, so I'll move ahead. So steps to solve optimization problem. So first step is problem formulation. So you somehow understand the problem and get it to that form which we decided: minimize over x, fx, x belongs to s. So you convert the problem in this form somehow. That is called problem formulation. We'll see some examples. Then you check the existence of solution. Now solving the optimization problem. So we'll uh, discuss three broad methods. One is graphical method, other is this, um, analytical method, and third is iterative method. So as we discussed earlier, uh, once we get the solution, we analyze the solution. Is it accurate or not? How much is it accurate? Is it within our limits or not? And can we get more accuracy? And then we also analyze the algorithm, the time complexity of the algorithm. Is it fast enough or not, etc. And once, based on the results of these two analyses, we decide whether to do this all over again. Do we redefine the problem statement, or should we go ahead and do all these steps again or not? So today we are going to see some examples of problem formulation. Some of the examples that we saw previously, we try to formulate the problem statement mathematically, and we also see some graphical methods to solve those problems. Okay, yeah, uh, that's what we'll do. So let's look at the problem formulation part. I'll put this in the next page, I guess. So yeah, problem formulation. So yeah, so first let's take that problem of bus stop. So yeah, so where should bus stop T be on PQ, road PQ, so that the distance from A and B of the bus stop is minimum. So I'll just write bus stop problem. Okay. First thing I write coordinates of A and B. So let's say PA is XA comma YA, PP is XB comma YB. I'll write it here. And now write the equation of line, let's say. let's say it is given. So mostly these things will be given. So ax plus by plus c equal to 0. So this is the equation of the line. Okay. So now uh, we look at the variables. Or I should put this in red, but this is important. So what are the variables of this system? Let's look at that. So variables is basically we want to see where the bus stop should be. So basically variables are pt or xt comma yt. These are the two variables. Now look at what are the objective function. Remember, we want to find three things. So constraints, variables, and objective function. These three things. So uh, objective function is distance should be minimum. Distance from PA to PT should be minimum. This should be minimum. Yeah, minimize this. And the last thing is constraints. Mm. So constraints are AXT. So basically, constraint in English will tell you that bus stop should be on road PQ. So this is what this is saying, that bus stop, the coordinates of bus stop should be on the road PQ. So this is the constraint. So let's write the mathematical program of this. So minimize over xt comma yt of distance PA comma PT plus distance of PB comma PT uh, such that AXT is subject to AXT plus BYT plus C equal to 0. This is our mathematical program. Beyond this, we'll see what algorithms to use to solve this program. But for today, this is how we write the mathematical program. Now, a similar objective function can be written for. Sorry, I'll go ahead a little bit. Go over a little bit to get this diagram. So I want to solve this problem of retail or commodity transportation. Okay. Again, so commodity transformation transportation is an important problem to solve, and this is different from the previous problem if you look closely. So I'll rub this off, I think. So we'll define some terms first. So let AI be the capacity of plant Fi. So let's say first plant has A1 capacity, second plant has A2 capacity, and let B be capacity, sorry, demand of retail store R. So here demand is P1, P2, P3. Okay. Now let's Cij will be cost of shipping unit weight of commodity from Fi to Rj. So let's say there is some cost associated based on traffic, let's say, or distance, and maybe the quality of road, etc. And it is called from this to this point, the cost associated is C11. Here it is C23. I'm not writing for others. It's like, but they are the same, like based on what what uh, plant you are and what the retail store you are. Now let's write the variables. So what are the variables? So as you thought, we wrote it anyways here. So variables are xij, which means the quantity going from F1 to RJ weekly. So based on weekly demand and supply, demand and the production capacity, what amount should you send weekly from F1 to F2 such that that is the best way. Now, second is objective. What is the objective? So this is where it is different from the previous problem. Here the objective is based on cost of the road. So for unit capacity, the cost is Cij. So for ijth, in and I plant and jth retail store, the cost for one let's say is Cij, and you're transporting X amount, so Xij, and you are doing for all INJs. So you sum it up. So this is the objective function. So we call this, let's say, total cost. Okay. Now we try to write the constraints. So how do you write constraints? So constraints, if you see, so shipped units, I'll first write it in English, then we'll try to convert it in mathematics. Shipped units from Fi should be less than uh, capacity of Fi. So shipped unit should be less than capacity of Fi, right? So if capacity is higher, let's say um, capacity is 10 and you are shipping more than 10, then it is not possible. So that is the constraint. So if you write it in mathematical terms, let's say from I to j, you are shipping xij, and from, if you see in the diagram, from f1 you are transporting fx x11, x12, x13. So basically from j is equal to 1 to 3. So this is the shipped units from fi, and this should be less than equal to the capacity of fi. Okay, sorry, capacity of fi, and I equal to here 1 and 2. This is how we write it in maths or mathematical notations, but it is actually saying the same like this. Then second is similar, shipped units to rj should be at least the demand of rj. So we can again write this in like, so shipped units to j is xij, I equal to 1 from 2 should be greater than equal to the demand of rj. Okay, and here j is equal to 1, 2, 3. Okay, so this, and there is one more constraint. You might think this is all, but all should be greater than equal to 0. So shipped quantities should not be negative. Basically, this is what it says for all I comma j. So yeah, now we are ready to write this in in mathematical program. So minimize over x. So we are clubbing all the xij's to x, uh, and objective function was this. So sigma ij xij dot cij, basically sum of all the commodities multiplied by their traveling cost, subject to some constraints. What are those constraints? This, and this. We'll write this. Uh, Sigma j is equal to 1 to 3 xij, sigma I equal to 1 to xij, and xij I equal to 1 comma 2, j equal to 1 comma 2 comma 3, xij greater than equal to 0 for all I comma j. So this is our mathematical program to solve this problem. So initially it looked a quite easy problem, but this is the problem statement that you have to solve, and math program that you have to solve mathematically to get the optimal solution. Now we'll look at, so we have discussed some ways to formulate problems mathematically. I want to look at this solution of optimization problems. And especially I want to look at graphical methods. So as I told you earlier, there are three methods: graphical methods, analytical methods, and iterative. So for analytical methods, you can recall uh, that minima problems in your class 10th or 12th, where you used to do df by dx equal to 0 and d2f by dx2 equal to, if it is positive, then it is uh, a maxima, minima, sorry. And if it is negative, it was maxima. So these the problems with which can be solved using some mathematical operators like these, you get the solution directly. You don't expend any computational time on that. So but we'll see that these class of problems are fairly simpler. So, and generally it is used for single variables only. So if you're able to solve that you know don't need that, you'll not spend much time in solving that problem, and it is good. The problem is simple. But sometimes that is not the case. For complicated problems, you cannot get analytical solutions directly. So we propose to the iterative methods, which is the main focus of this course. Like we want to try to solve such statement which can only be solved through iterative, and analytical methods fail on that. But there are some problems so simple that you can just look at the graph and decide what is the problems. And it's good to look at some of those problems to get an intuition of how the functions or the work, how to think about optimization problem. So we'll go through it, and instead of writing on this page, I'll try to show you some slides. So I hope the slides are visible. So we'll try to understand how to solve a optimization problem through graphical methods. So let's say first look at a very simple problem of function with one variable. So this x minus 2 whole square plus 3 is the function, let's say. So it has minimum at 2, and minimum function values is 3. So it's a very simple problem. You just plot the graph and you see, oh, at 2 it is minimum, and you can also know the value of the graph. So it's a simple problem, and it can just be solved by using graphical methods. Then there is other problem, minus x square, where maximum is x is equal to 0, and minimum function value, sorry, so it should be maximum function value. I think so, it's a mistake here. So maximum function value is also 0. Rest of of them are slower. And please note, there is no the minimum does not exist for this of this objective function. Now there's one more saddle point. So there's something called saddle point, and if fx is equal to xt, so uh, if you see on one side of this point, the objective function value increases, while on the other side it decreases. So these are very important points in an optimization problem or in an objective function to have, and we try to look for these points and use it in some ways to get to the solutions. So, and sometimes some algorithms also get stuck in these places, so we have to avoid those stuck like those algorithms which get stuck in these places. So it is good to know what a saddle point is. uh, Now we'll move to, and this is a typical nonlinear function which multiple peaks and multiple valleys, and let's assume it is going to infinitely positive on both sides. So you can see that the black dots that you see are the local these points called are minima, but they are called local minima. So actually, if you see the objective function on both sides of this or these points go are bigger than the point itself, but it's not the smallest point in the whole objective function. The red point is the global minima, and it turns out that it is very difficult to differentiate between local and global minima. So, because they both have almost similar properties, if you consider the differentiation is 0 and also the double differentiation is negative there. Uh, So it's a difficult to okay. Okay, so it's difficult to differentiate between these 2 points. So double derivative is, I think, positive at the global at these minimas, and so very difficult to differentiate between two. There is a separate class of research which goes behind finding the absolute global minimas. But in the algorithms that we'll try to study in this course will be trying to find local minima, and that is sometimes. Uh, Good enough, like good enough for most of the applications or the problems that we have. So let's go to two function of two variables. Um, so this is just a classic quadratic function x1 square plus x2 square. It has minimum at 0 0, and minimum value is also 0. You can see there are a bunch of circles at the plane. So if you take a horizontal plane and you cut this part, and cut this part, you'll find circles which have same objective function values. And if you plot it, it's called and contour plots. So that is one way to look at this. So as you can see, these circles, all the circles have same values which are indicated like 0.1, 1, 2, 3. So this is you just by graph you can see what the minimum is. uh, then there are some other kinds of variables like this x1 times exponential minus x square minus x2 square, and it has one valley and one peak. So just by analysis of the contour plots, you can see that the minimum value is at minus 1 by root 2 comma 0, and maximum is at 1 by root 2 comma 0. Then this is one more function of two variable, but here instead of the contour plots being circle, it is ellipse. But still you can find the minima of such a function. Uh, and then there is a very popular function called Rosenbrock function in optimization literature, which has contour plots like this as shown in the graph, and it has minimum at 1 comma 1. I just wanted to show you this before because we'll use these functions later on in the series quite a lot. So just by looking at the graphs at 1 comma 1, you can see that I mean, it's difficult to see, but people have, if you analyze this graph in detail, you can get the minimum of this function. So now let's see a typical nonlinear function in two variable, so which has multiple peaks and multiple valleys, and an optimization problem can be thought of as intuitively thought of as you try to put a marble at some point and it falls and goes to some valley like this. So depending upon where you put your marble, it will go to different local values every other time. So that's why this is what our algorithm does. It starts with an initial position and then tries to goes to the lowest possible point. So and that's it uh, from the graphical methods. Now let's come back to the pen and paper. And now I will that is most of the thing that I wanted to teach today. I just want to now give you a course overview, what we are going to study in our future lectures. So if you want to differentiate the optimization problem, we can differentiate in a way like let's say constrained and unconstrained problem. So basically, this is minimize over x fx, x belongs to s. And unconstrained means x. Now there is another class, continuous and discrete, in which x takes discrete values like integers or binary values, and here the variable is continuous, uh, belongs to, most of the time it belongs to r, or r to the power n, and r is real number set. And then there are stochastic and deterministic. So in stochastic, what do we mean by stochastic? When data is not, data that we are given is not fixed, or not a, uh deterministic function, it is a probabilistic function, not deterministic. On the other hand, deterministic is there is no randomness. So to give an example of this, let's say we had that problem of plant and retail store. So we had some values of their uh, capacity and uh, demand, right? Uh, B1, B2, B3. Let's say instead of being some deterministic value, these value uh, can occur based on some probability. So let's say these value have some mean and variance, this A2, B1, B2, B3, then this problem becomes stochastic. So what are we going to study in this course is unconstrained, continuous, and deterministic problems only. So deterministic, continuous, and unconstrained. We'll later on maybe do some other lecture series for constraint, because that is also important. But for now, we'll stick to this. And one more thing, the algorithms that we will study, uh, as I told you, it can do a local optimization or global optimization. We'll only study local optimization algorithms, because global optimization, it's difficult and it's like out of the scope. But local optimization actually is, most of the people in most of the application, people, the algorithms that are used are local optimization problems only, and it is useful in many ways. So this is, we'll not study global optimization. And finally, uh, talking about some topics. So this is where the lecture ends. I'll uh, just tell you what we'll do in next few lectures. So we'll do some mathematical uh, preliminaries in the next few lectures. Then we'll do optimization for one variable, and then we'll do optimization for multiple variables. So in mathematical preliminaries will be linear. We'll do some linear algebra, some calculus, and also some only features which are useful for this course. We'll try to do them, delve into that linear algebra, calculus, and a little bit of I think real analysis, like how to deal with real numbers, and optimization with one variable will set up the base of the course, and we'll use those principles for multiple variables in the next. So these are not three lectures, this will be set of lectures, which list is given on the flyer, you can have a look. So that's that. uh, uh, I'll try want to end at that. And if you want some books for references, so I'll advise you to have a reference of like two references I will give. There is a Fletcher R practical methods of optimization, and there is Anocidal J and right M. Their book is called Numerical Optimization. These books are good. You can refer to these books. Yeah, that's it. Any questions from your side? Okay. Uh, okay, so if you don't have any questions now, you can also ask the question on that email thread that I have. Yeah, so yeah, Arun is asking where can I access this note. So I'll send these notes to you on the email thread, and from there you can see the notes. Or maybe I'll also send the slides as well. So I'll update the PDF of the slides also. Okay. Any other question? Okay, so I think I took a lot of time. I wanted to finish it in 1 hour, but I went overboard. So maybe I'll have to plan my next lectures properly. But yeah, so I think I'll end the meeting now. Yeah, and that's it. Thank you.